Hello everyone, welcome to today's lecture. Emeka Udenze is on the line, and today we're going to be talking about calculations in chemistry. Let's take it away from there. In chemistry, there's a lot of, to understand chemistry, we do a lot of mathematics. So my main goal, objective in this lecture is to take us through a few of those mathematical problems for us to gain the proper mathematical skill at this level of class for us to understand our chemistry better. So the three learning objectives we're going to be achieving at the end of this class include to express numbers using scientific notation and perform calculations with them. We'll express result of measurements and we'll express result of measurements and calculations using the correct number of significant figures, and finally we'll perform calculations involving percentages. Those are the three learning objectives we're going to achieve at the end of this class. Let's take it away. So first of all, we're going to start talking about scientific versus standard notation. Let's first of all define what is standard notation. The standard notation is the everyday way of writing numbers using decimals, using commas. So if you use decimals and use commas to represent numbers in hundreds and thousands, those are the regular way of writing numbers in everyday. Example, if I want to write 2,568, that is, I'm going to put comma here. So this is the standard way of writing this number. Or what if I want to write 28.4? This is another way of standard way of writing this number. What if I want to write, let's say, 250? This is the standard way of writing, particularly when the numbers are very small. Using the standard notation works really very well. It's an easy way of writing the numbers. Now, but when those numbers get even bigger, it becomes a little bit trickier the way, because we can't keep writing the number of digits and digits and digits. So scientists found a more convenient way to write those numbers. So that brings us to scientific notation. So scientific notation just simply involves a more convenient way of writing either very large or very small numbers. And those numbers are represented in the term m times 10 raised to the power of n. Now let's try to define what those are. Now in this case, the m, not n, the m here represents the non-exponential term. It's the non-exponential term, which is a non-zero number. The non-exponential term, it cannot be zero. It's a non-exponential term. And this number is between, it has to be between 1 to 9. It cannot be, it can't be 10. The number has to be between 1 to 9. So those are the two places that, numbers we can use. So it can be, or let me put it this way, it has to be in between 1 to 10. Let's just put it 1 to 10. It cannot be 10, but it can be 1, but it can't be 10. So anything in between those two. And you must put a decimal number. It has to be written with decimal. It has to be written with decimal. It has to be written with decimal. On the other hand, n is the exponential term. N there is the exponential term. This exponential term can be positive or negative. Now, if the number in question, let's call the number x. Let's just call the number x. We're talking about, like writing my x the other way. Let's call the number x. If x number is less than 1, that means it's 0.0 something. If x is less than 1, what it means is that n will have a negative value. N will be negative. Then on the other hand, if x, the number you want to express in scientific notation, is greater than 1, what it means is that n will have to be a positive value. It has to be a positive value. So that is what we're going to see. So in this case, I will rather put comma here so that I don't confuse you. I'll rather put a comma here. Let's see. Yes. so that I do not make it confusing. So, yes, or semicolon, that will help. Right. So let's see how that works. We have some number. I have some numbers that I have to my left here. Let's look at it. So first of all, I have this long number. Look at this number, it has a lot of digits. And let's try to see if we can express this number in scientific notation, right? So first of all, if a whole number is written, or if a number is written without decimal, right? The standard, it has a decimal. But what it simply means is that the decimal is at the end of it. So what it means is that the original position of the decimal is at the end. But we'll now move it to the standard position. What is the standard position? The standard position is the position to the right or to the left to the non-zero digit. So the first non-zero digit, right? Either to the right or to the left. So look at what we're going to. So we're going to move this number. Let's move this number now. So of course, this is the original position. This is the original position. And then this is, let's move it. So the standard position is going to be somewhere here. So this case now, it is to the right of the first non-zero number. So this will be the standard. Let me call it STD. Standard position. Now let's move this number. Let's move this and adjust the position of this decimal. That's basically what we're doing. So we're going to say 1, 2, 3, 4, 5, 6, 7, 8, 9. So basically, let's count. So this will be 1, 2, 3, 4, 5, 6, 7, 8, 9. So we counted. So the decimal shifted to 9 times. So if you want to represent this, remember, in this case, you will not drop any non-zero digit number at this point. So what we're going to do is to rewrite this in terms of this guy. And to do that, what are we going to have? I'm going to say that it will be 2.021, because these are zeros, we don't have to write them again, times 10 to the power of 9. This form is what we call the standard notation of this number. We can also do same with the second one. And in this case now, remember what we said? We said, look at earlier, if the number itself, in this case, our number had x, which represents all of these numbers. If it is greater than 1, oh, I didn't put 1 in that one. If it is greater than 1, oh shit, I didn't put it, please. If it's greater than 1, oh, I didn't realize that I didn't put that. If it is greater than 1, wait, let me write that well. I have to write it well. If it is greater than 1, we said it's going to be what? The n, in this case, the n is going to be, let's see, we counted to 9. So this 2 times 10 raised to the power of 9. So here, the n is 9, and it is what? A positive. N is 9, but here, in case, it is a positive. So that will what we have there. Now, look at this one now. This one now is 0.00. This is less than 1. So we're going to be expecting that the n value here is going to be what? Less than 1. Let's see what. So in this case now, whereas for the positive numbers, we move to the left. For the negative one, which is less than 1, we're going to be moving it to the right. Let's see what we're going to do. The same thing. So we're going to move from here. 1. The standard position is going to be here. So we're going to move it 1, 2, 3, 4, 5, 6, 7. So it's going to be, and in this case, we're going to say negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7. So we have our n to be what? Negative. That's what we have here. And we have it to be equal to 9. So what we're going to put is 2.021 times 10 to the negative 7. This representation will be the scientific notation for that number. That's what we call the scientific. Then this is the scientific notation for this number. So what we're simply going to be doing in this type of work is that you able to identify the standard position and move the number in the appropriate direction. Let us now solve some problems. It says write the following numbers in scientific notation. again, the instruction didn't tell you to round off, so do not round off. Let's do it quickly. So what we're going to do here is we're going to, this is the decimal place. It's already shown to us. It's not at the end. So move it to this point, remember. So we're going to say 1 and 2. So if you're going to rewrite this, it's going to be 6.82. You're going to bring all the digits back, but this time times 10 to the what? This is 1, 2. 2. The second one, again, you're going to move backwards, so it's going to be, the position will be here. So we want to move this. So it's going to be 1, 2, 3, 4, 5, 6. 6. So that's going to give us 8.61 times 10 to the negative 6. Remember, this is negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. The next one there will be, here the standard position is here, but we're going to move it to this point. And if you move again, it's going to be 1, 2, 3, 4, 5, 6, 7. So this is going to be 3.89 times 10 to the power of 7. And finally, the last one here, the standard position is here. So we're going to move it to, we're going to move it this way to the left. So it's going to be, and we're going to return all the digits. So here, there are 4 digits here. Because of the decimal place, we're going to move it 1, 2. So this is going to be 2.48 times 10 times 10. Well, let me write that 10 very well. Times 10 to the power of 2.480. We have to bring all the decimals. That's 10 to the power of 2 mils. That is how we express that. So in this case, if you've not been asked to round off, if you're not specifically asked to round off, you are not supposed to round off. Let's go to the next thing. Now let's do another reflection. In this case now, he said the following numbers are written using scientific notation. Write them without scientific notation or in standard form. So we're not working backward like we did before. So what they're simply going to do is to maintain this digit and move it backward. So what I'm going to do is that I'm going to, first of all, since this is 6, I'm going to start with by writing by 6.43. So what I'm going to do is to move this now to the right by 6. So it's going to be 1, 2, 3, 4, 5, 6. So now, since there's no more number left, we're going to be adding 0 to it. So at the end of the day, the number is going to be 6, 4, 3. Remember, no decimals at this point then, no decimals. 6, 4, 3, 0, 0, 0, 0. That is what the number will be. And then again, you work opposite for the second question. Again, what you're going to, in this case, this is easy. When you have this, what you simply need to do, you just add 5 zeros in the front. Start a number, start this with 0 point. We start with 0, add a decimal, and then count the whole numbers, the whole decimal into 5, and let it be in the front. And that's it. This is easy to do. So what you do, just add what? 5 zeros. Add 5 zeros to the front. In the front. I will tell you that was easy for this one. So just do, since this is 5, 0.000, 1, 2, 3, 4, 5. And then what you do, you don't add the non-zero digit number, which is 2501. Since this 0 is buried there, it has to be shown. So that is how you bring this back to the standard notation. So this is how you do this. So it's important for us to practice to know how we can do this. We'll now go to the next thing we need to talk about too. Uncertainty measurement. You see, numbers in measurement represent 2 things. Whenever you do measurement in number, there are 2 things that are represented. The first thing you present is what? Is the certainty of the measurement, and one number that is an estimate, or we call it the uncertainty or the precision. So whenever you make a measurement, you're going to have a particular number of digits that will be uncertain. And this uncertainty are usually due to limitations of measuring devices or some human ability to read it. People see things in different ways. So we're going to be using this ruler here for this kind of example. We're going to be using this ruler to see how that works, for us. Now, here, this ruler, we have a ruler here and we have a rectangular piece of wood that we want to measure. So this is a ruler. Let me start. This is a ruler itself now. This is a centimeter ruler. This ruler is a centimeter ruler. So to read this number, there are the first things I need to do. The first things first I need to do is that I need to know the smallest measurement, which we call the least scale division, or the smallest scale marking. I need to know those lines. Look at these lines. Now we have this line from here to here. What is it? So if I can determine those lines, it's going to help me to read those numbers. So let me first of all determine that small number. So this least scale marking is the first thing that I want to determine here. So what am I going to do to determine? So the least scale marking of this will be, first of all, let's do it. If you count from here to here, look at this number from here to here. There are 10 small lines if you count it to 1. If you count from here to here. So if you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you count again, to be 10. So what we're going to do is to say, okay, let's call those blocks or lines. Let's call it lines or divisions. So if there are 10 small markings, 10 small divisions, represent 1 centimeter. Because from here to here is 1 cm. Another 1 cm interval, another 1 cm interval. What it simply means is that one small division will be 1 centimeter divided by 10. That will give us 0.1 cm. So what it simply means is that the smallest scale marking between these two small lines is 0.1 cm. We are sure about that. But what if we have it in between these numbers, in between small numbers, like in between the first two markings? Does it mean we have it in between the first two markings or in between any markings? It becomes difficult to read. At that point, we introduce that uncertainty. So let's measure let's now measure the length of this block to use that to explain this. So the length of this block now, let's see. If I can read the length of this block, I would say this is 9.5, 9.6, 9.7, 9.8. From my eye, I'm seeing 9.8. So I can say the measurement of this number is between 9.8 and 9.9. That's what I would say. It's in between those two. So if I'm going to choose any number in between these two, I'm still close to this measurement. Right? So then if I think it's in between, what am I going to call that? How am I going to estimate that? The best way to estimate that is to first figure out the precision of that rule. And how do we do that? How we do that is that when you get the least scale marking division, else the LSD or the SSM, you estimate it by past an extra digit. So we're going to add one more digit. So I would say that the precision of this meter rule, precision, will be, remember, the precision is different from the least scale marking, least scale division or the small scale marking. So what I'm going to say is that since I got this to the LSD to be 0.1, if I move it by one decimal place again, I'm going to get 0.01 cm. So what it tells me is that if I want to report my digit for this measurement, it has to be in 2 decimal places. So reporting it as either 9.8 or 9.9 is not correct. Then if I assume that this number is in between line 8 and line 9 here now, so I will say my measurement could be 9.80, 2 decimal to match the precision of the meter rule. Some other person can say, or is 9.85. Some other person can say it is 9.84. Now, look at what happens here is that these other digits are barely estimated. You cannot be precise about those measurements. And that is why you have to, first of all, determine the precision of any instrument you want to use before you use that instrument. The idea is that the precision of the instrument will enable you to report that number to the correct number of significant digit, the correct number of digits. So when you do your calculations, you know how to put them. So it is very, very important for us to know how to do it, particularly by the time you get into the next class after this and begin to do the labs. So what does that mean? These two numbers are the certain numbers. We call it the certain. These two numbers are certain. The first two numbers are certain. But the third digit here represents the uncertain digit. So this third digit, this is also the uncertain digit. This is also the uncertain digit. So this is also uncertain. So in this measurement, the third digit is the uncertain number. So this is what we mean by uncertainty in measurement. Let's take an example here. It says, now I've already explained this in the previous slide. So uncertainty or precision of the instrument is estimated by determining what that small scale marking that I already told you, or the least scale marking. You divide it by 10 or estimating it one more digit back forward. That's what we do. So let's see this example. It says, write the measured value with the correct number of digits for a graduated cylinder with water at exactly 2 ml. So, and this particular digit has the smallest scale marking, the SSM, to be this. Remember, if the SSM is already 0.1, we need to figure out, first of all, the precision. So the precision of this instrument will be to move this by an extra digit. So what are we going to do? So this precision will likely be 0.01 mil. So what this simply means is that if I want to take the measurement at 2 mil, I can't just say it is 2 mil. I have to say it is. I have to make sure that the 2 mil agrees with the number of decimal places. So the measurement of this is going to be 2.00 mils. This is the accurate measurement of this cylinder. So I can't say 2 mils because it is possible for you to get a number in between those last two digits, although estimated is very, very important in measurement. So let's now begin to talk about significant figures in the next concept here. Significant figures. So significant figures, again, will not be enforced in this class, but it's important for us to begin to figure out what this means for us. So in writing significant figures, simply rules of counting zeros in numbers. Again, one of the ways of managing numbers. That's exactly what it is. So those rules include number one, all non-zero digits are significant. That's what it's telling us. So if I have a number like this, 2, 5, 3, 4, 2, we have 1, 2, 3, 4, 1, 2, 3, 4, 5. All these numbers, none of them is non-zero. So this is 5 significant figures. 5 significant figures. Again, it says zeros not preceded by non-zero digits are not significant. And we call these zeros what? Leading zeros. So any zero at the back of a number is not significant. So not at the back, at the front of a number is not. So example, if I have 0.0052, the number of digits I have here is just 2 because this number is in front. This 0 is in front. So this is going to be 2 sig figs. Now, look at this one. This one is interesting. It says zeros that are located between the non-zero numbers are significant. So we call them what? Buried or confined or captive zeros. If a zero is in between two numbers, that zero is significant. So if I have example 2002, you see the zero is buried in between these two. So the total number of digits is actually 4 sig figs. And finally, it says zeros that are located at the end of a number are significant. Zeros that are located at the end of a number are significant. If, look at the word if there is a decimal place present. If there are no decimal places, it does not count. But if there are decimal places, it counts. Okay, let's see an example. This one has, let's say 2000, has no decimal place. So what counts here is only 2. So here it is 1 significant figure. But if there are decimal on it, right, it counts. If there are decimal on it, everything at the back begins to count. So that kind of number is actually called trailing zeros. So the ones here will not count, but the ones coming after decimal are going to count. So if decimal is there. So, and I have this example to show. So if I show you this, so look at what this shows here. So here now, if you look at this now, here, this is the leading zeros. The leading zeros, what, are not significant, right? Yeah, so they are not significant. So this is the leading zeros, not significant. So this is not significant. So this is not significant. Then what about the captive zero? The captive zeros are always significant. They're always significant. And then what about the trailing zeros? The trailing zeros are significant with decimal. Here, these zeros are, in this case here now, it is significant because that's decimal. So they're significant with what? Decimal. These zeros are significant with decimals. So those are the common type of zeros we're going to be seeing. So let's try to practice a few of these in this page. So it says, state the number of significant digits in each of these measurements, and we're not expected to round anything off. So here, let's count. This is what? Buried zero. See, is buried inside. All of them count. So here we're going to have how many digits? We're going to be having 5. If you count it 1, 2, 3, 4, 5, it's going to be 5 sig figs. Look at this one. These are zeros that are in front. Leading zeros. Leading zeros are not significant. So here we're going to only count this one. So it's going to be 3 sig figs. What about this one again? This is leading zeros. Here is going to be 1 sig fig. Sig fig. Here, buried zero. This zero is buried between these two numbers. Everything will count. This is going to be 3 sig figs. And then what about this one? This one now. So this one has a buried zero, which counts. This one has trailing zeros, which do not count. The trailing zeros here do not count because there are no decimal in this number. So let's count the one. Let's get the one that counts. This count, this count, this count, this count. So this is going to give us 4 significant figures. And then for this one, there's a decimal here. The leading zeros do not count, we know, but because there's a decimal, these 3 other zeros count. These trailing zeros count because there's decimal place here. So what are we going to do? We're going to count. We're not counting this one, but we're going to count 1, 2, 3, and 4. So here we actually have 4. Okay, 4 significant figures. So here we have leading zeros and trailing zeros with decimal. That is what we have for. And finally, in this case, we have a trailing zero, but there is a decimal here. Because of this decimal, all these guys are going to count. So here, if we count everything, let's count. Here it's going to be 1, 2, 3, 4, 5. So where we're going to have 5 significant figures. That is what we have in this place. So rounding numbers. Let's talk about rounding numbers. Rounding number is another way of managing numbers, right? So that you don't have to keep writing all the digits. At times when you do calculations, it gives you very rational numbers that it was almost endless. So that is why we have to apply this in the first place. So to round numbers, if first of the non-significant digit to be dropped is greater than or equal to 5, all the non-significant figures are dropped and the last digit will be increased by 1. On the other side of the coin, if the first non-significant figure to be dropped is less than 5, all the non-significant figures are dropped, and then the last remaining significant figure is unchanged. You don't touch it. So what does that mean? Let's see. Let's take an example here. Look at what I mean. What it means is that if you look at these two, now, it says we should round this off to what? 4 digits. So 4 digits means 1, 2, 3, 4. At this point, that's what we want to stop. We want to stop at this point. But look at this number. This number now is what? 6. And 6 here is greater than 5. Since it is, that my greater is not facing the way I want. So it's greater than 5. So to round it off, what are we going to do? What are we going to do? We're going to say, okay, we're going to be dropping 6 alone because we want it to be 40. Dropping 6. But since 6 is greater than 5 or equal to 5, so here is greater than 5, we're going to call it 1 and add it to the 3 and drop the 6. So here, we're going to round this up to 4 digits to be 18.74. That is how you do that. The next one will be the opposite. This is to 2 digits that we want to keep it. In 2 digits, that means we want to drop it at this point. But look at the number following it. The number following it here is what? 2. And 2 is less than 5. So we're not going to change anything. So we're going to drop the 2 and 5 and leave this number to be 5.9. We're not going to do anything because this number is less than 5. So this is how we do rounding. Again, another way to manage numbers as well. So let's try to do some reflection question 4 here. Say round the following to 3 significant digits. Let's do it. Only 3 digits alone. So the first one here, we're dropping this number, and so you're dropping this number. This is less than what? 5. This is going to be 9.4 to 3 digits. Remember, that's what we're doing. The next one, here we're dropping this number. What are we dropping? We're dropping this 0, right? So again, these zeros are all significant because of this decimal place, but we don't care. In this case, we're dropping it, and it's less than 5, so it's going to be 1.63 times 10 to the negative 3. Now, do not touch the exponent. Do not touch the exponent when you are doing this. You don't have to touch the exponent in this case. Let's do this one. Look at this one now. So this one, remember, these zeros are not significant, but these ones at the back are significant. But since we're doing it in 3 digits, our interest is 1, 2, 3. So we're going to be stopping here. And the 0, 0 is not up to 5. So we're going to say 0.0. How many do we have? 1, 2, 3, 4, 5. 0.0000. 1, 2, 3, 4, 5. 3, 0, 0. Or if you want to make it into the scientific notation, remember, what we're simply going to do is to take this and put it here, make it to come here first. So it's going to be, this becomes the standard position. So it's going to be, remember, there's no decimal there. I don't want to confuse you while I'm doing this video to think that there's a decimal there. Well, let me make sure that okay. So it's going to be 3.00, because we have to maintain that these digits are significant, times 10. Since this is 5 here, 5 zeros in front, we will negative 5. Then the next one here, we're also going to take it to 3 digits. So it's going to be, we want to take it to this point. What it simply means is that we're going to be dropping every number and moving it over there. Now, but if you look at this number now, some students will be tempted to say it is 188. No, it's not 188, because this number here is actually 18,750. This is 188. It's not the same thing. So this is tricky. What you do in this case is that when you make this to be 8, because there are 2 other digits here, there's no decimal. You're just going to put 0, 0. So this is actually 18,800. Will be the best way to write this, or you put it into the standard notation to be 188 times 10 to the, this is 1, 2, 3, 4 to the power of 4. And the final one here will be, we're going to 3 digits again. This is what's greater than 5, which is 7. So add it here, so this will give us just 2.66 grams. That is what we're going to get here. So that is how to do rounding numbers off. And again, like I know most of you would have come across this or done it before, but it's important for me to go through them once again and brush it out so that you can, at least begin to remember those stuff as we move on with this class. Now, the next thing we're going to do with rounding numbers and operations, right? At times we do mathematical operations. Again, significant digits are not enforced in this class, but I usually tell students to round numbers up to 3 or 4 digits, no matter what calculations they did. But it's important for us to know how to manage number, right? So there are rules involved. What is the rule? The first rule involved here is that the answers to this kind of problem, when you are multiplying 2 numbers, the final answer will have the same number of significant digits as the number with the smallest digit. So the rule here is that the number with the smallest digits will influence what the final answer will be. Let's count. There are 1, 2, 3, 4. There are 4 significant digits here, and there are 3 significant figures here. So what it means is that 3 is smaller than 4. We're going to multiply the number. If you go to your calculator and punch this in, if you punch this into your calculator, you're going to get a number 19.09952. That's what you're going to get. Now, since we want to decide, do we keep writing this number? And sometimes when you do this in the calculator, these numbers are irrational. They're endless. But we want to manage it. The best way to manage it is follow that rule. So our final answer is supposed to assume a 3 significant digits. So what it means now, we're going to round this off to 3 significant digits. So and that will be, what is it going to be? Since we're going to be dropping the rest, this is greater than 5. The final answer will be 19.1, so that it will match the smallest number. That is the rule. The same thing goes for the next one we're going to be talking about here. So multiplication and division follows the same rule. Here, if you put it in your calculator, you're going to be having 4.45 4565 dot dot. The number will not end. This is a typical rational number till infinity in your calculator. So this till infinity. This sign represents infinity. It doesn't end because it's an irrational number. But if you look at this now, this is a 4 significant figure. This is 2 significant figure. So our final answer is supposed to have 2 sig fig to match the one with the smallest number of significant digits. So what are we going to do is to round this off to that. So to round this off to 2, what are we going to do is to drop the rest of the number. And since this is equal to 5, we're going to make this to be equal to what? Final answer will be 4.5 will be our final answer, rounded to 2 significant digits. On the other hand, the rounding for the rule rather for addition and subtraction are different. For addition and subtraction, the rule purely focuses on the number of decimal places. You know, in the previous one for multiplication and division, it focuses on the number of significant figures. In addition and subtraction, our focus will be based on the one with the least amount of decimal places. So the final answer will assume the number of decimal places of the number with the least number of decimal places. What does that mean? Let's count. This is 1, 2, 3, 4. This is 4 significant figures. We're not counting significant figure, we're counting decimal places. So this has 1, 2, 3. So this is 3 decimal place, DP. This is 2 DP. Oh, that's not DP. So if you add this with your calculator, first of all, you're going to have 15.065. Now, since we want to make this to be, this is in 3 decimal places, but we want it to be in 2, right? What it means is that we're going to round it up. We're going to be dropping this 5. And since this 5 is up to 5, equal to 5, what we're going to do is to drop it and increase the other number to 15.07. Now, this agrees to 2 decimal places, which is what this one has. The same thing will happen here when you're subtracting. If you subtract 10.78 minus this, we're going to have 7.88. But again, we have 2 decimal places here. You have how many? 1 decimal place here. So what it means is that we're going to drop this 8 to make it 1 decimal place. And when you do that, since this number already is greater than, this 8 is greater than 5, we're going to have 7.9. This is now 1 decimal place, agreeing with the term with the number with the smallest number of decimal place. That is how we'll do this type of rounding. We now get to the next concept we're going to be talking about, which is the exact numbers. Now, some exact numbers are those numbers with no level of uncertainty. They're usually assumed to be infinite number of significant digits, and therefore we don't even write them at all. It is usually part of a defined relationship, like in this case, in between quantities. If you say 1 kilogram is equal to 1,000 grams, so 1 kilogram equal to 1,000 grams is just assumed to be an exact number, a definite number. It can also be counting stuff, so counting numbers obtained by counting individual objects. Example, 1 dozen of eggs is equal to 12 eggs. We can't have 12.01 eggs or 12.2 eggs. We can't. It can also be part of what? An equation, some constants an equation, whereby you have numbers that are part of an equation, like this 5/9 that is found in this formula, used to convert Fahrenheit to Celsius. So the 5/9 here represents an exact number, so it does not have any level of uncertainty in them. So these are what we call the exact number. It's important for you to know those as well. Now let's talk about using your calculator. You see, the use of calculator in this class is very, very important because a lot of students struggle with this, because putting exponents in calculator can be very challenging. And different scientific calculator, like I said in this class, we need a simple scientific calculator, a simple scientific calculator. And using a simple scientific calculator, you need to know how to impute your numbers in scientific notation, or put it clearly, the exponent. So it's important for us to for you to get accustomed to the calculator you use, to know the symbol of the exponent, and do not use the caret sign. Now, students do this. The caret sign or caret symbol in your calculator does not represent, is not exponent. That simply shows raised to the power. Do not use it. Do not use it. Do not use that. So most calculators will come up with these common symbols I'm going to show you. Exponential simply means times 10, a number that is not 0 times 10 to the power of this, like we already said. The common symbols you see in calculator is either EE or single E, EX by exponent, times 10 raised to the power X, which I like using these two terms last. Some calculators do come with this and this. Those are the ones I recommend for this class. And I know if you were there in the first day of the class, I already told you guys, the calculator I showed you use these last two terms. It's easier for you to do. So it is important for you to know how to use your calculator and understand that exponential is different from raised to the power. So that is why I'm actually doing this, talking about this particular concept now. So let's try to put this in a calculator. Now, if you follow the rule of significant figure, right? This is 2 sig figs. This is 2 sig figs. Again, remember, significant figures are not enforced in this class, but it's important that I let you know that. So there are two sig figs, 2 sig figs. So the calculation will be basically in 2 sig figs. So we don't have any problem with that. If you multiply, if you do 2.5 exponential, don't put times 10. Just do 2.5. Press this guy in my own calculator. It shows up as this 2.5. I press this guy, and then I'll press 3 times. I press 1.4. I press this guy again, and press 10 negative 2. If I put that in my calculator, it will come up with 35. That's what it's going to give me. So 35, or if I want to make it 2, scientific notation, 3.5 times 10 to the power of 1. So this is what we're going to do. So it's important for you to know how to use your own calculator so that you don't run into the trouble of doing all the work right, but at the end of the day, missing your last answer because you're not coming. So if you have questions about this, please do make out time to talk to me either in class or in the office hours. Now let's talk about more complex operations using multiple operations. In this problem now, we're going to be utilizing multiple operations. Multiple operations. So if you look at this question now, let's look at that question clearly. In this question now, it says 4.5 times exponential 23. Exponential, I didn't say times 10. 4.5 exponential 23 times 8.7 exponential negative 6 divided by 2.79 exponential 8 times 5.800 exponential this. So for us to solve this problem, it's important for us to remember what we call the BODMAS, the rule of operations. Usually, you have to split them. You do the up, you do the down. So I'm going to use put bracket here to do the one up. So if I do the one up first and impute that in my calculator correctly, look at what's going to happen. So if it's independence on its own, what it means is that if this is 3 significant figure and this is 2 significant figure, if I put it in the calculator, my answer is going to be 3.915 times 10 to 18. Remember, because I'm doing the top, between 2 sig figs and 3 figs, the rule of multiplication says that my answer has to be 2 sig figs on the top. So what it means, but since I'm not done with the mathematics, it's not important at this point to begin to drop any number. So what I'm going to do is to do a checkmate of the second digit here. So this yellow underline simply tells me that there are 2 sig figs in the upper solution, that I have to report the upper solution into sig figs. Now I do the lower one. If you do the lower one, look at what so here it will be 3 significant figures, and this will be 1, 2, 3, 4 significant figures. What it simply means, if I do this solution, my answer should be in 3 sig figs. And when I do that and multiply it, it gives me in my own calculator to be 1.6182 times 10 to the 26. Again, my answer here should be in 3 sig figs because of this, in 3 significant figures. So what I'm going to do, I'm going to do another checkmate. Since it's going to be in 3, I'm going to say, okay, this is the 3rd digit here. So what it simply means is now, if you are now dividing 3.15 times 10 to the 8 divided by 1.6182 times 10 to the 26, right? Exponential 26. If you're dividing these numbers, what it means, if you have 2 sig figs and you have 3 sig figs. What it means is that the final answer should be in what? Should be in 2 sig figs, the one with the least number, which is on the top, the 2 sig figs. So if I'm doing that, what I'm going to do is that I'll now take my calculator, punch in the numbers again, the top one divided by the lower one, and I'm going to come up with the final answer to be 2.419 times 10 to the negative 8. However, I want my answer to be in 2 sig figs. So what I'm going to do, I'll round this off now to 2. So to round it off to 2 significant figures, I'm going to drop the rest of the number this way. And since this number is not even up to 1, the one to be dropped here, it's not up to 5, sorry, it's less than 5. So my final answer is going to be 2.4 exponential, which is times 10 to the negative 8. This becomes my final answer. So it's important you know how to do this. Okay, that seems to have colored it that much, but I'm gonna make it look better. So okay, so I just want to make it look better. So that is how to do problems with multiple operations. Okay, all right. So we now go to the next thing we need to cover here. Will be solve problems with addition and subtraction and write answers. It says, for reflection, it says solve the following addition and subtraction and write the answers to the correct number of significant figures. Let's do this real quickly. So here now, there are, let's see, how many decimal places? There are no decimal place. There is 0 decimal place here. There is 3 dp here. No, there's 1 dp, sorry. 1 decimal place. And here, there is how many decimal places? 1, 2, 3, 4. There's 4 dp. So if you add that thing up, it's going to give you 2810.7006. So to round it off to the correct sig figs, the one with the lowest number, it will be this one, no significant figure. So we're going to write this without significant figure, and that will give us to be approximately equal to, without sig figs, that will give us 281, because this is greater than, remember we are dropping all this is greater than 5, we're going to be 2811. And the final one here will be 9.2369 minus 4.35. So here you have 4 decimal places dp. Here you have what? 2 dp. So what you're going to do here is, if you subtract this from this, it gives you 4.8869. Now we want our answer to be in 2 decimal places. What it means is that we want it to be stop at this point. So, and again, this number is greater than 5. So to drop it, we're going to have approximately 4.89. And this is in 2 decimal places. Remember, this one has 0 decimal places. So that is how we do those problems. So to finish this lecture, we're going to be talking about something that will be needed just as a reminder how to, make percentages. So the percentage simply means expressing a number in 100 parts or group of 100 of such items. So here the equation usually is that you take the part, you divide it by the whole total and multiply it by 100. So I'm going to use the example of my college here. It says Yakima Valley College enrolled 5,219 male and 4,369 female students during the 2024-25 academic year. It said determine the percentage of male and female students enrolled for that academic section. So first of all, we need to determine the total. So for the males, we know that the total is 5219. For the females, we know that 4,369. If you add these two together, we're going to have 9,586 will be the total. So the percentage of male in this case will be part of the male, which is 5219 divided by the total 9586 times 100. And the percentage of female will be the same thing. Part of female will be 4367 divided by 9586. See, the total is the same times 100. And if you do this for this one, it's going to give you about 54.44% of males, whereas this one will give you about 45.56% of females. Another way you can determine the female is that already, since you had this one already, you know it is over 100. So what we can do, another way to determine the percentage of female will be, say the 100 part of minus the number of male part, which you already determined first. 100 minus 54.44 will still give you 45.56. So if you get the first part in a decimal, in percentage, if you get the percentage of the first part, the remaining part will be 100 minus those parts to give you the rest, because it is always in 100 parts. Okay, at this juncture, we've come to the end of this class, and I want to thank you for listening. Bye.